So momentum is equal to mass times velocity. However, angular momentum is an object with that's moving in an orbit or is spinning. And the equation for that is radius times velocity times mass. So this is representing the two types of angular momentum, orbital angular momentum and spin. As you can see, we have the sun, which is Faith, and Andrew, the Earth, is orbiting around her. At the same time, the Earth is also spinning. So this represents the two types of angular momentum.
There are three parts to angular momentum: Lx, Ly, and Lz. Lx, as shown by Faith, is when something is around the x-axis. Ly, as shown by Nicole, is when something's spinning around the y-axis. And Lz, as shown by Dawna, is when something spins around the z-axis.
So angular momentum has a direction. And one nifty trick you can use to find the direction of the angular momentum of an object is called the right-hand rule. Basically, the way this works is you take your right hand and you curl your fingers in the direction of motion of the object. Then you point your thumb outwards, and whichever direction it's pointing in is the direction of angular momentum. So the interesting thing about angular momentum is that it's conserved. So we know that angular momentum is equal to the radius times the mass times the velocity. So what it means to be conserved is basically that if you change, for example, the velocity, then either the radius or the mass has to change as well in order to compensate for that. So if we make an object move faster, it either has to somehow weigh less, or it has to move closer to the thing it's orbiting around. So either mass or radius must decrease to compensate for an increase in velocity.
To illustrate the concept of the conservation of angular momentum, a turntable can be used. When spinning on a turntable, if you push your arms out wide, the radius is very large, and so your velocity must be smaller. By bringing your arms in, velocity is increased to compensate.
Now, as if that all wasn't weird enough, angular momentum is quantized, which means you can only have certain amounts of it. It won't be one portion of angular momentum and then 1.5 portions. It will only go up by certain amounts. Now, you don't usually see this in large objects, but on the small scale, it becomes very important.
If you know one part of angular momentum, Lx, Ly, or Lz, you can also know the total angular momentum. But you can't know two parts of angular momentum at the same time.
Dawna, a secret scientist, is investigating the value of agent Lx. She finds it to be 2. Now, she's off to investigate the value of agent Ly. This one's 1. Now, let's see what Lx is. You'd think it would still be 2, but Lx and Ly don't commute. The value has changed to 3. Let's check again. What's this? It's still 3. Maybe Ly has stayed the same. But no, it's changed because we've measured out X.
My credentials. Well, I have a doctorate in biology, chemistry, astrophysics, engineering, neuroscience, basket weaving, Native American arts and crafts. What else do I have a major in? My final major is one that I studied for a long time, and my dissertation was quite interesting. I'm sure you would love to read it. It turns out that I have quite a knack for staring at things for long enough periods that they tend to explode. Yeah, I can show you right now, look.